तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Good morning. This is the third lecture in electromagnetic fields for EEE students. Last two lectures we had covered vectors basically, and this lecture I want to introduce the first application of vectors, namely Coulomb's law. So, we had already seen Coulomb's law before in many courses, so I do not have to go into it. If you put two charges Q1 and Q2, then the charge Q2 feels a force from the presence of charge Q1, and the force is on a line joining the two charges, and it is pointing away from Q1 when it is applied to Q2. The same two charges apply the force the opposite way, that is Q1 feels a force from charge Q2. It is an equal and opposite force. How large is this force? Well, if this distance, if we call this R12, when I label things like R12, I mean put the foot of the vector at 1, draw an arrow to 2, and that vector is called R12. Then the force is proportional to the strength Q1, it is also proportional to the strength Q2, and it is inversely proportional to the square of the distance, that is, it is inversely proportional to R12 square. This is the well known Coulomb's law, and I am sure you have met it many times before. This is a force, and forces are vectors, which means that this is the magnitude of the force. The force also has a direction, and the direction of the force is given by the direction of R12. When I put a cap on top of any symbol, it means unit vector along the direction of that symbol. So, the force is along R12 and it has a magnitude that is proportional to Q1 Q2 over R12 squared. Now, the proportionality is completely arbitrary. There are coordinate systems, namely the CGS system, where we would actually write F is equal to Q1 Q2 over R12 square. But in this course we will be using the SI system, the standard international system, and in the standard system this proportionality constant is not 1, it has got a value. So, the full equation looks like F, which is a vector, is equal to this proportionality constant times Q1 Q2 over R12 squared along the direction R12, and for SI units this proportionality constant is called 1 over 4 pi epsilon 0. This, as I told you, is completely arbitrary. In another coordinate system, then this proportionality constant would be different. For now, all that is important to know is that epsilon, which is called the permittivity of free space, has a value which is 8.8 into 10 to the minus 12, okay. And if you look at the units that it must have, you can take r square to this side, q1, q2 down. So, what will you get? You will get that 1 over epsilon has the units of newtons, meter squared per coulomb squared. So, epsilon naught must have the units of coulomb squared per Newton meter squared. More conventionally, it is defined in terms of capacitance, but we will come to that later. All right. So, this is a vector equation. It defines a vector f in terms of another vector and some scalars. Now, this f, which is the electrostatic force, f is a function of q1, the location of q1, q2 and the location of q2. Okay. Now, how strong is this force? For this, let me go back to Feynman lectures. Robert Feynman, one of the most famous physicists of the 20th century, he wrote 3 volumes, Lectures of Feynman, which are probably the finest introduction to physics that has ever been written. And in volume 2, he talks about electricity and magnetism. I strongly suggest you read chapter 1 of volume 2, and I am going to take an example from there. You know that charges come in 2 types. There is positive charge and there is negative charge. Positive charges include protons, ions. Negative charges include electrons. And any human body contains enormous number of both. Now, supposing humans did not have equal number of electrons and protons. Supposing we had an excess of electrons. How much? Let us say we had a 1% excess of electrons. All right. And to simplify all our mathematics, I will assume a human being weighs 100 kilograms. All right. So, roughly 1 kg worth of protons equivalent charge in electrons is excess. Okay. Human density is 1 gram per centimeter cubed. So, 1 kg contains 1000 centimeter cubed. Each centimeter cubed contains around 10 to the 23 protons or electrons. So, we will say 1% corresponds to 1000 times 10 to the 23 electrons. All right. Now, what does that give us in terms of a force? Supposing you had human being, 1% excess electrons, and this human being is standing below another human being who is also a 1% excess electrons. So, each of them has 10 to the 26 electrons, that is 10 to the 26 more electrons than protons. So, we can apply Coulomb's law. Let us say they are about 1 meter apart. So, we will say that the force magnitude is equal to 1 over 4 pi epsilon 0 into 10 to the 26 times the charge of the electron whole squared, because both of them have the same charge, divided by the distance, which is 1 meter whole squared, and this force should be newtons. Okay. We already know what epsilon is. Epsilon is 8.8 into 10 to the minus 12, 4 pi is 12. So, if you combine the two, this is around 10 to the minus 10. Charge of the electron is 10 to the minus 19 coulombs. So, if you put it all together, what do you get? You get 10 to the 26 times 10 to the minus 19, that is 10 to the 7 whole squared, 10 to the 14 divided by 10 to the 10 minus 10, which is 10 to the 24 newtons. I think there is 4 times 10 to the 24. All right. 10 newtons is the weight of 1 kg. That is, the force of gravitation is 10 newtons per kilogram. So, this force can lift 10 to the 23 kilograms. And do you know what the weight of the earth is? The mass of the earth is 10 to the 24 kilograms. So, if two of us happen to be having an excess of electrons of 1%, the force between us could lift the earth. That is how strong this electric force is. It is unimaginably strong. We can compare it to the gravitational force, because if you have two people, they attract each other gravitationally and they also interact through electrical forces. So, supposing I take two electrons, there is an electron and another electron, they are separated by a distance d. The force due to gravity is the gravitational constant times the mass of the electron squared divided by d squared. This is the force with which one electron attracts another electron. This is gravitational attraction. The electrical attraction force due to the electric field is 1 over 4 pi epsilon 0 E squared, the charge of the electron squared, divided by the same d squared. So, we can work out how much stronger the electric field is compared to the gravitational field. How much is it? Well, the d squared will cancel out. So, what you get is F electric divided by F gravitation is E squared over 4 pi epsilon naught divided by g times me squared. As before, the electric charge is 1.6 into 10 to the minus 19 coulombs. The mass of the electron is 9.1 into 10 to the minus 31 kg. Now, the gravitational field, the universal constant of gravitation is 6.7 into 10 to the minus 11, and the units are again got from here, which is Newton meters per kg square. Now, you can see I am going to take 10 to the minus 30 square, 10 to the minus 60, and then I have a 10 to the minus 11, and I am going to take it all to the numerator. I have here 10 to the minus 19 times 10 to the 10. So, a huge number is going to come out. Well, you can work it out, and what you find is that this is of order 10 to the 43. That is, the electric force between two electrons is 43 orders of magnitude stronger than the gravitational force between those electrons. Now, naturally, the gravitational force is proportional to mass, whereas the electric force is proportional to charge. So, if you took a heavier particle with the same charge, you will get a better answer. Well, how much better? If you took the proton, proton has a mass which is around 2000 times, well 1800 and something times the electron, all right. So, in that case, this ratio gets divided by 2000 squared. So, then you will find that Fe over Fg will be like 10 to the 43 divided by 10 to the 6, which is 10 to the 37. It does not get any better than this, because the proton is basically a heavy particle. Most of our body is built out of units which are the weight of a proton. So, this is why Feynman says that the force due to electricity is a billion times stronger. Okay, 4 billions in a row, because a billion is 10 to the 9. You put 4 of them next to each other, 10 to the 9 to the power of 4 is 10 to the 36, and this ratio is actually 10 to the 37. So, the electric field is enormously more powerful than the magnetic field, than the gravitational field. However, in our normal experience, there is no electric field. In fact, if you look at the ancient records, you will find they talk about gravitation, but they do not talk about electricity. They knew lightning, and the Greeks knew a little bit about amber. They knew that amber could be rubbed and then it will attract things. They knew about some magnetic materials, but that was it. This force, that is a billion times stronger, is missing. It is just not there. So, where does it go? how is it that when you get to larger and larger scales, the electric field becomes less and less important, whereas as you get to larger and larger scales, the gravitational field becomes extremely important. Okay, let us take a look at that. There are several answers that are given. Okay. Let us take them. Answer 1, equal number of electrons and protons. So, the result is, if you have an electron and you have a proton and they are both close to each other, then far away this electron is, let us say this is a positive charge, it is attracting that charge, the proton is repelling that charge, and so there is a very slight force only. And so, all these huge forces that are being exerted by the body, they all cancel. Well, there is a problem with that argument, and to see that problem, let us work out what happens in such a case. Supposing I have a charge q and I have a charge minus q, that is, I am thinking of the proton and the electron, and they are separated by a distance d. I want to know what is the field due to this proton and electron combination far away. Now, if you look at this, you can construct what the forces will be. You will draw a straight line to this point, and the force will be away from q. We will draw another straight line connecting minus q to this point, and the force will be towards minus q. Now, the forces will mostly cancel. However, if we write out what the forces are, you can see that this distance from the point P to minus q is a larger distance than from the point P to plus q. How much larger? Well, we can draw perpendiculars and see that this distance is equal to this distance plus a little extra, whereas this distance is equal to this distance plus again a little extra. So, the distance from minus q to P is equal to distance from plus q to P plus this quantity. And how much is that quantity? Well, it is a standard calculation. You have done it in your optics when you do interference. If you take this angle as theta, that angle is the same as this angle theta, and so you can say that the difference in distance is 2d sin theta. So, this d sin theta. The total distance is d. So, this distance is d sin theta. So, the distance from minus q to this point P is the distance from q to this point d plus this extra distance, and this extra distance is nothing but this d sine theta. Sine is nothing but the opposite side over the hypotenuse. Okay. So, now if I want to find out what the force is, well, the force, I am only calculating the force along the radius. There is actually a force also in this direction. We will work that out later when we work out what the electrostatic potential is. But the force along the radius, so F sub r is equal to 1 over 4 pi epsilon 0 q over, I will call this r1 squared minus q over r2 squared. So, this is r1, this is r2. In other words, the force along the radial direction is due to the fact that one charge is nearer, one charge is further away. So, the 1 over r squared is not the same. So, I can write down what this will come out to. The radial component of the force is 1 over 4 pi epsilon 0 times q over r1 squared minus q over r2 squared times, of course, the charge of the at the point P. There is a charge small q, which should also be multiplying here. Now, I can write these in terms of each other, because I have already written the distance from minus p to p is the distance from plus p to p plus d sine theta. So, I will write that out. It is 1 over 4 pi epsilon naught q over r1 squared minus q over r1 plus d sine theta whole squared times small q. All right. Now, what does that mean? I know that I am looking from at a point far away. So, this r1 is much larger than this d. So, I can say r1 plus d sine theta whole squared is approximately equal to r1 squared plus 2d sine theta times r. All right. That is, I am neglecting the d squared sine squared theta, okay, because it is very small. Then I substitute that here and I expand. So, my Fr becomes capital Q small q over 4 pi epsilon naught times 1 over r1 squared times 1 minus 1 over, I have pulled out an r1 squared. So, 1 plus 2d sine theta over r1. This is a very small quantity, because d is small compared to r1. So, I can expand this, and I will expand it in place. When I take it to the numerator, this 1 plus 2d sine theta over r1 will become a 1 minus 2d sine theta over r1. So, it becomes 1 minus 2d sine theta over r1. The 1 will cancel out, and what you are left with is q over 4 pi epsilon naught. There is an r1 cubed and a 2d sine theta. So, ultimately, what have you gained? The q over 4 pi epsilon naught r1 squared is Coulomb's law. You have an extra term that goes like 2d sin theta over r1 times F Coulomb. So, the fact that you had electrons and protons close together buys you this factor. It means that if electrons and protons are on average d distance apart, then at a distance r1 the force is smaller by this factor. But does that explain why gravitation dominates? Let us see the numbers. We have the numbers here already. We have that gravitation dominates by a factor of 10 to the 37. Now, typically electrons and protons are 1 angstrom apart. So, d is of the order of 10 to the minus 10 meters. We are talking about a distance of 1 meter away for this calculation. So, r is 1 meter. So, what does that factor give you? It gives you a factor of 2d sin theta over r is roughly equal to d over r, which is 10 to the 10. Now, 10 to the 10 can reduce 10 to the 37 to 10 to the 27. But 10 to the 27 is still a very large number, which means that this talk about having equal numbers of electrons and protons does not explain why gravitation dominates. If it were really just that, then electromagnetics would have dominated and we would never have noticed gravitation. We would have all been floating around like charged dust, and we would never have noticed that there is a huge planet which is trying to pull us to itself. Okay? But that is not what happens. Now, there is an answer to this, and the answer has to do with a slightly different explanation than this. And to explain this, we have to really go back to all the forces. If you look at the universe, there is gravitation, that is the weakest force. Then you have magnetism, that is the next weakest that we know of, electricity, and then you get to the nuclear forces. And these are the strongest forces we know about. There may be stronger forces than these, but we do not know. Now, it turns out that when we talk about electricity and magnetism, we do not take into account nuclear forces. When we talk about gravitation, we do not consider electric fields. Sometimes we consider magnetic fields, but not often. In fact, gravitation is by itself, electromagnetism is by itself, nuclear forces are by themselves. That is how you will find it in textbooks. And the reason is there is such a large range of force here, each is unimaginably stronger than the other, that they cannot compete. If you see electric forces, it means nuclear forces have cancelled completely. If you see magnetic forces in normal materials, it means the electric forces have cancelled completely. And if you see gravitation, it means all these forces have cancelled completely. So, how does this cancellation work? Supposing you take a gas containing charged particles. So, there are positive particles and negative particles, electrons and protons. So, they all are busy exercising Coulomb's law, and Coulomb's law is 10 to the 37 or 10 to the 43 times stronger than gravitation. Now, such a gas, for example, is found in astronomical nebulae. Okay. nebulae that are heated by nearby stars, they are all charged. So, you will have enormous amount of charged particles in those gases, and so you would imagine that electric forces are dominating, but that is not the case. Now, what happens inside is these charged particles adjust themselves to other charged particles. By that I mean a charged particle has only as much energy as its temperature allows. So, it is rattling around, and if it has 100 degrees of temperature or 1000 degrees of temperature, that limits the amount of rattling it can do. So, if a very strong electric field develops, all of the particles move, and in moving they cancel that electric field, and they do this at every point in this gas, everywhere, till finally there is no electric field at all. Now, we know one case of this, which is a conductor. We know that inside a conductor you cannot have an electric field, you cannot have forces. The same idea happens here as well. In fact, if you look inside a gas, you can show, I am not going to show it, but you can show that the force due to Coulomb actually decays like e to the minus r over lambda. It does not go as inverse square law at all, it goes exponentially small. This value of lambda depends on the material, it can be very large, but usually it is very tiny. So, now if you now take this model and you try and compare our body magnetic, gravitational versus electric, the answer becomes very different, because you are no longer comparing inverse square law to inverse square law, you are comparing exponential decay to inverse square law. When you do that, you can ask, when does e to the minus r over lambda divided by r over lambda squared become approximately 10 to the minus 37. If that happens, then the 10 to the 37 extra number will cancel out. Well, you can plot this, and what you find is the following. If you plot e to the minus r over lambda divided by r over lambda squared versus r over lambda, this is a logarithmic plot, so semi-log, you will find more or less a straight line that intersects 1. It starts out at 10 to the 37 or whatever number. So, this is 10 to the 37. It reaches 1 at around 80 to 90. So, around 10 to the 2, around 100 r over lambda, the electric field has become as weak as the gravitational field. So, it depends really on the value of lambda. For most materials, lambda is very small. For conductors, it is angstroms. It is small. For a weak conductor, it may be micrometers. So, within a centimeter, the gravitational field has taken over from the electric field. Now, this is really the reason why we never see the electric field in large scale phenomena. It is very rare to see them. The moment you have electric fields from many particles, the particles adjust to cancel out that electric field, but particles cannot adjust to cancel out the gravitational field. The reason is there is no positive gravitational field and negative gravitational field. all masses attract each other. You do not have a negative kind of mass which repels. So, gravitational field is phenomenally weak, but it always adds. The electric field is phenomenally strong, but it cancels. And as you go to larger and larger scales, the electric field becomes unimportant. So, we can draw a diagram now explaining the various forces. If you had nuclear forces, they form the nucleus. The kind of scale length on which they work is 10 to the minus 15 meters. Once you get away from 10 to the minus 15 meters, the nuclear forces become attenuated. That is, they tend to adjust and cancel themselves out. The electric forces they work at the scale lengths of chemistry, that is at angstrom distances. So, due to nuclear forces we get elements. Due to electric forces we get chemistry. We get molecules. We also get metals and other kinds of properties. The magnetic forces they have much longer scale lengths. In fact, they can have galactic scale lengths. So, they are very large scale lengths. But they are very weak, much weaker than the electric forces. For example, the Earth's ionosphere is dominated by the magnetic field. The entire solar system is dominated by the solar magnetic field. The entire galaxy is dominated by the galactic magnetic field. And finally, you have gravitation. And ultimately, the weakest force, gravitation, becomes the strongest force, and it actually forms the universe. So, there is a very peculiar kind of ordering. The strongest force cancels itself out earliest. The next strongest cancels itself out next. The next strongest works up to a galactic scale length, and gravitation finally conquers everything. And in this picture, we are looking here. We want to understand electric forces and we want to understand magnetic forces. Now, I have anticipated myself several times, but still I will repeat just to make sure I have got my point across. We have the Coulomb force, it is a vector, goes like 1 over 4 pi epsilon naught, charge 1 times charge 2 divided by r12 squared along the direction of r12. This is the definition. This is the definition if you have two charges. But supposing I had a collection of charges and I want to know the force on a charge here. So, I have Q1, Q2, Q3, Q4 and I have a charge Q. What is the force on charge Q? Well, Coulomb not only found this law, he also found out how this law works when multiple charges are present. He found out that you ignore all but one, find out what Coulomb's law says about that one. Now you ignore all but another, find out what Coulomb's law says about the next. And then vectorially you add them up. The result is the total force. If you want to write this mathematically, what it says is the force is equal to 1 over 4 pi epsilon 0, this charge q times q1 divided by r1 squared along r1. So, this distance is called r1, this is r2, r3 and r4, plus 1 over 4 pi epsilon 0 q2 over r2 squared r2 plus 1 over 4 pi epsilon 0 q3 over r3 squared plus 1 over 4 pi epsilon 0 q4 r4 squared along r4. Now you can see that q is common, so I can pull it out, and when I do that, I can write the formula as follows: F is equal to small q over 4 pi epsilon 0 summation I equals 1 to 4 capital Q sub I r sub I unit vector divided by r sub I square. This summation is simply saying substitute I equals 1, substitute I equals 2, I equals 3 and I equals 4 and add up all the results. Now this interesting formula is known as superposition. What it really is saying is the following: it is saying that whatever interaction there is between this charge small q and this charge capital Q1 is not affected by the presence of other charges. Let me give you an example where this would not be true. Supposing I had my charge Q1, this is my Q, and supposing the medium in between were affecting Coulomb's law, and supposing the medium, its properties change because of Q2. For example, the medium has an epsilon. We have been writing epsilon naught, but the medium may have a different epsilon, and this epsilon may change due to Q2. If epsilon changes, it means the force between Q1 and small q is a function of whether Q2 is present or Q2 is absent. In that case, this would not work, this would be wrong. But luckily, Coulomb's law has been verified, and it is known that it is correct, that if you do this experiment in vacuum, that this superposition rule is accurate to some 20 digits. I will explain later just how they come up with such statements, but in a certain sense Coulomb's law is the most accurately known law in physics. There is no law that they know better. For instance, we know the speed of light to about 10 digits. We know the gravitational constant to about similar number of digits. We are not at all really sure whether we understand the law of gravitation, but we know the power of 2 here correct to 20 digits. So this is the most accurately known, most precisely tested theory that we have in physics. Okay. So we have come up with superposition, and we can put point charges, and I already used this idea without telling you when I calculated the force due to a dipole, because I had a charge q, I had a charge minus q, and I had a charge small q, and I chose to calculate this force first and then this force next. That is only correct if superposition is true. However, that is a very simple example. Supposing I had a cloud of charge, lot of charge, and it is distributed over a region, and I want to know what is the force on a charge q somewhere else. Well, this equation is still true. The force is equal to 1 over 4 pi epsilon naught summation I equals 1 to capital N q sub I Ri divided by Ri squared. But this number n may be very large, maybe it is 10 to the 23. If we are talking about all the charges in a small amount of a metal, then this will be a very large number, and we cannot practically carry out such a sum. Luckily, just when we struggle to carry out such sums, we have a new way of looking at things which makes things simple. If there is a very large n, then we can make a little box inside the volume. This box would have sides which are very small, and we would count the number of charges, amount of charge inside the box. So we could take box of size delta, and we could plot, or we could calculate the amount of charge in it. So we could make a table, and we could say take delta of 1 centimeter, 1 millimeter, 1 micrometer, and so on, and work out what the charge is. Now obviously the charge will become less and less. However, if you plot charge per unit volume, that is, you calculate the charge and divide by the volume of this cube, divide by delta cubed, well, what do you expect? What we expect is like this. This is delta, this is q over delta cubed. For very large delta, the fact that the charge is not uniform, there may be more charge out here, less charge out here, we are not, our cube is spanning all these different regions. So you will expect some variation. Then as the delta becomes small, the distribution of charge inside that small region is more or less uniform. So we expect that the charge will stabilize, that is, charge per unit volume will stabilize. Then when this box becomes very small, so small that the number of charges inside this box becomes only a few, then you will start having noise. This is the kind of picture any experimentalist will tell you is present. We want a box around there. We want a box where we are not inside the noise, but we are not corrupted by the fact that our box is too big. If we take a box like that, we can replace a sum on individual charges by a sum on boxes. And we all know what a sum on boxes is. This is nothing but 1 over 4 pi epsilon 0 volume integral charge density over the volume. I will continue this next time, but the idea is basically here, and we will continue next time.